Hello, everyone. I hope you can hear me. If you do, please write something on the chat. And also, Ida, I have given you permissions to activate the microphone as well. Okay, great. Thank you, Sandra. Let's wait a couple of minutes since we're having a little bit of trouble getting Berhan on board. Okay, here's Erhan. Hello, Erhan. Good afternoon.
Yeah, now I can see. Hi, guys.
Oh, okay. Hello, Erhan. Just to make sure, can you try sharing your screen? I think you must be able to do that.
Let me see. 1 second. No, I don't have any. Share is not enabled for me.
Okay. Okay, let me see how we can handle that because Oscar cannot join us, and in the end, the Ikerlan is the ones that
my
create the
solution.
sessions.
So my recommendation would be this. Can you share screens? I guess you can, right?
Yeah, I do.
Okay, so I already uploaded the webinar into work package 10 folder.
Okay, that's great. So yeah, I'll
So maybe
just that's
you'll share
perfect.
it. Yeah, that would work.
Okay. Okay. Just give me a second. I'm on it. There it is. Okay, I have it now.
All right.
So, well, just to let you know a little bit of the I don't know if you were present when we made our webinar, but the idea is that you start presenting anything that you have prepared, and then we'll leave some minutes for any questions if anyone from the audience has any. Okay.
Sure.
Okay, so I'll start sharing my screen. Here's Boolean. Okay. I hope you can see it now.
Yes, I can. Thank you.
Okay, that's great. So, well, first of all, let me welcome everyone to the second webinar of the Zero Defect Zero Waste project. In this time, we're going to speak about digital twin applications for industrial thermoforming. It's going to be presented by Dr. Erhan Turan from Simularge, and well, from now on, I give the floor to you, Erhan. So, please.
Thank you. Maybe you can also switch the modes because we just see the.
Oh, okay.
No,
I'm
no,
sorry. Yeah, I know what you
no problem.
meant.
No problem.
I'm sorry. Not better now.
Yeah, thank you.
Okay,
Appreciate it. All right, now next slide, please.
there we go.
All right, so today I'll be talking about some digital twin applications for industrial thermoforming, and this webinar will be related to ZDZW project, which is Zero Defect Zero Waste project supported by European Union. And this is the short summary of our webinar for today. I'll be briefly talking about what thermoforming is and its application areas. Then a little bit of digital twin will be explained. Then I'll be giving a couple of details about the thermal side, so the thermal modeling of thermoforming in our project. And one industrial use case will be given at the end of this talk. Now, maybe can we move to the next slide, please? So let me talk about myself first. So this is Erhan. I'm the CTO and the co-founder of Simularge. I have a mechanical engineering background. I did my PhD back in 2010 in Boğaziçi University. I've been in ETH Zurich, Bosch Company, as well as G Aviation. I did a lot of engineering stuff, both in the academia and the industry. Before joining Simularge, I was focused on developing jet engine designs for Airbus and Boeing aircrafts. And starting from Simularge, our main focus is creating digital transformation solutions as well as digital twins using our own technology. So my interests are generally for industrial computing, numerical science, as well as digital transformation AI. Next slide, please. Let me also talk about Zero Defect, Zero Waste project. So this is a project funded by Horizon. It is related to this Twin Green and Digital Transformation Call. There are 27 partners from different countries, all European. We have also SMEs, we have institutions, we have universities combined in a single framework. The duration is 36 months, and we are right at the center of this project. 18 months already passed, and we have a little bit of information and initial results from our work. So Simularge is a part of this community, and the reason that ZDZW project is initiated is that there are a lot of problems with the waste. Typically, waste can occur if there is a quality problem during the production process. If the manufacturing parameters are not set, then we see quality issues. That is one area that we'd like that as a project contributor, we would like to help the community. Another part is when we do detection to understand how defects work, sometimes we do destructive detection processes. And the idea is if we can create non-destructive detection algorithms or system, it will be really useful because we don't have to waste the part that we are trying to solve. And to address this challenge, there will be a couple of work suites, or let's say inspection suites, will be created among this project work scope. Our goal as Simularge is helping the thermal inspection suites, but we also have, like, I don't know, visual inspection suites or some other suites as well. And you can see here from the slide as well, typically destructive testing techniques or inspection technologies are really time consuming. It requires a lot of investment. It is also requires cost, but we would like to keep it short, and we would like to give a high tech a chance to help this area. Maybe we can move to the next sections. Right. As I said before, we will be using advanced AI techniques on engineering approach to solve this problem. Yeah. So this is a general overview of the ZDZW project. So there are 6 pilots, and all of these pilots will be focused in 1 or 2 inspection technologies. The pilot they're involved with is the pilot 2, where we're going to help thermoplastics manufacturing getting better using digital tools. And you can see, as I said before, there are inspection suites, there are process monitoring diagnosis. We're going to create a digital ecosystem in which the project contributors will be creating their own applications, and under a marketplace or on a general storage area, this will be accessible all of the members of the member communities. Okay. So let me talk about thermoforming. So typically when we produce parts from plastics, thermoforming is not the first choice. Plastic injection or blow molding is among the top alternatives to create parts out of plastics. But thermoforming procedure also has its own use. I mean, in reality, if the pieces are large or they cannot really be created using typical plastic injection operations, we use thermoforming. In a nutshell, thermoforming is not a single process. It has some stages. The first stage is typically heating up the piece so it gets softer and we can give it a shape. Second stage is where we apply a mold under vacuum or maybe in an open or closed chamber setup. Using this mold, we can give the desired shape on the softened material. Then we wait, which is the cooling part. And in the cooling part, our goal is to keep the temperature as low as possible so the shape that we gave to the material stays as it is. And then we have this trimming process where we chop off the additional parts. You can see there are 2 types of thermoforming. The first one is the thin gauge. It's generally used for packaging of foods or similar sizes. And the one that is more of a industrial use case is the heavy gauge. It is used in liners, both sometimes even the front section of the ATM machines. We can move to the next stage. Next slide. Okay, as I said before, there are a couple of stages of thermoforming. The first stage is where we heat up the material. So our goal is to soften the material. It's a thermoplastic material. It could be polypropylene, polystyrene, or ABS materials. In a normal heating process, we use generally electrical heaters. They're like ceramic or quartz heaters. And using the radiative heat transfer mode, we can just apply some heat input onto the surface of the plastic sheet. Using diffusion within this volume of the thermoplastic sheet, we can create a higher temperature material. When it's hot enough, we can move to the forming section. In the informing section, as the image from Wikipedia showing to you, we apply the mold. The mold can be used within a chamber, within the closed control chamber, where we create a vacuum to support the molding operation, or even in this simple example where we are creating a thermoform-based luggage. You can see it also works in an open environment as well. In normal conditions, people are not really focusing in the cooling section, but during the forming stage, we also need to wait for a couple of seconds, even sometimes a minute or so, just to make sure the temperature is below the critical temperature that we call glass temperature. At the end, trimming, we just remove the additional excess parts, excess stuff from the part. And the good thing about this is these parts can be recycled and start from the initial phases of thermoforming, where we create this uniform plastic sheet. So it's not a waste of time. It is really important. Please, next slide. Before we proceed, I would like to also give additionally short introduction to digital twins. In a nutshell, digital twin was first introduced by Michael Greaves early 2000s. The idea is to create a real live objects copy in a virtual setting. That means if I don't know, I have this mouse, I would like to create a copy of this a virtual mouse in which all of the motions, all of the actions that I apply on this real device can be simulated in a computerized environment. So in a nutshell, digital twin is a combination of a mathematical modeling in which we might have chemistry, we might have physics laws, we have some engine mathematics, and it also is a data point. So we need to make sure data is also collected from the environment for the same part or same workflow, same system that we are trying to investigate. So model alone or data alone is generally not enough to create a digital twin. For that reason, I also put a section here to tell you guys what a digital twin is not really composed of. If you have a three-dimensional image, which is a fancy representation of the part there we are looking into, it is not a digital twin. It's just a three-dimensional object. Or if you collect sensor data, if you have a bunch of sensors, bunch of altimeters or some PLC data is flowing into a dashboard in which we can monitor what is going on in a factory, in a shop, or in a car. That is also another digital twin. Sometimes people call it digital shadow. It's like a mirror in which we know what's going on in our system, but it's not a digital twin. It's just a virtual representation of the real life that is occurring in real time. In a similar fashion, a three-dimensional result in which we have a simulated mathematical model that is also another digital twin. So we need to understand that digital twin requires both a mathematical model and also data. And next slide, please. All right. So the digital twins have a lot of applications. I just put 3 examples here. You can use a digital twin to create a optimized furnace. I mean, for a furnace, you can maybe initially create a virtual model that works for a perfect environment. Then by collecting data from the furnace, you can just calibrate your system. Then it gives you the potential to optimize your furnace. You can use a metal forming. For instance, in this here, you're using a press machine to give a shape in a steel object, and by collecting data from the press machine, you can also create a digital twin and improve your product quality. Or typically, and most of the people probably familiar with this approach, predictive maintenance can be also incorporated with digital twins. You have a data, you have a model, and using these, you can create a forecast to understand where the maintenance should be really applied on the machine. Next slide, please. All right, so back to thermoforming. In this webinar, I'll be mostly focusing on thermal aspect of thermoforming. I know thermoforming is also the molding stage as well as the trimming stage, but it is really up to the thermal stage of the process. If you know how to control the behavior, the heating behavior of the thermoforming process, then it really helps you to control the quality of the final product. So the reason that we need heating is, as I said before, we would like to soften the material itself. You can see one example here, the PS material, the one that is shaded with the blue color, loses its strength like 1,000-fold if you go from, I don't know, 50 degrees to 150 degrees. You can see an additional temperature input of 100 and 150 degrees gives you the potential to give a shape into the thermoplastic material. These are taken from J.L. Thorne's book. You can see Understanding Thermoforming is a very good book, by the way. And you can see using this softer material, now you have this so-called forming window. You can see the bottom figure there. You see there's a point where we heat the material and then we form the material. In order to form the material, we need to make sure this temperatures within this whole volume of the plastic sheet is close to each other. So if you know that the top surface, bottom surface, the inside of the volume is close to each other, we say we are within the forming window. For that reason, controlling the temperature input and making sure the inner section and outer section are almost identical or almost uniform is useful, just to make sure our thermoforming operation is really running smoothly. On top of that, since the shapes that we are trying to produce are not simple shapes, they have a lot of complex features, some sections that needs to be pretty good, that needs to good control because it's a end user product. We also apply zonal heating. Zonal heating means some part of the plastic is heated more than the more than some part of the thermoplastic. That means we would like to have some hot zones and cold zones, and that also complicates the problem a little bit further. Okay, we can move to the next section. One example here, and you can see here both heating process with zonal heating in mind. You can see there are some very red tiles and also some soft or a little bit dark red tiles. These tiles means some part of the heating process is creating a hot zone and some part of the heaters are creating a cold zone. And a simulated result is like here, 2D simulation. You can see we are seeing two sections which are hot on the left and the right section, and you also see a section which is colder. And you might ask, why do we do that? I mean, what is the reason to create a non-uniform temperature profile? And the reason for that is when we move to the next stage, we apply the mold, which is a structural forming operation. These hot zones are the location where the mold is initially contacted with the thermoplastic. So we need to make sure where the mold touches for the first time on this material is softer than the remaining part of the material. For that reason, we are creating a non-uniform structure, and this makes the quality of the end product better. Yeah, we can move to the next stage, the next slide. So this is a very simplified version of the heating characteristics of thermoforming. You can see we have this plastic sheet at the center in the gray color, and on the top and the bottom we are applying heating through heater elements. The heater elements could be ceramic heaters, quartz heaters. Some of them are cheaper, some of them are more expensive, but for instance, quartz are more expensive, but their response time is really improved compared to typical ceramic heaters. Within the thermoplastic, which is thin, by the way, I mean, at most it could be like 4 millimeters, 5 millimeters, 6 millimeters at most. Even if it's thin, there is also diffusion within the body. That means even if we apply heat on the surface of the thermoplastic, within the plastic sheet, conduction is occurring. So I don't want to go too much of details into the physical equations, but what is critical here is that radiation effect on a plastic sheet is nonlinear because the equation itself has a power of 4 of temperature, and the effect of conduction is linear. So in a nutshell, when we do zonal heating as well, meaning some of the heaters are hotter, some of the heaters are colder, adding the effect of nonlinear radiation, this problem becomes really complex. So for that reason, we apply modeling, we apply finite element analysis, we apply some integral rules to make sure the temperature on the surface can be calculated. And this is the core of our digital twin solution. Next slide, please. All right, I said there are heaters, bunch of heaters. The previous example, we had like 200 heaters at the top of the furnace and the 200 additional heaters at the bottom of the surface. That means we have 400 different heater elements. That means we need to understand how these heaters really behave. You see how these heaters really look when you look closer to them. In a typical setting, these heaters might have 500 watts or 1000 watts of power depending of their type. But the critical graph here is the watt versus temperature. So you see, if you apply 500 watts, you get a different temperature value. If you apply 1000 watts, you get a different temperature value. That is also not linear. So if you're on the low side with a low wattage given onto the heater element, you get like, I don't know, 300 or 400 Celsius as a temperature value. But if you go above and behind, like close to 1000 watts, you get 800, 900, or 700, depending on the type of the manufacturer or the heating element. So you need to incorporate this change into your digital twin design as well. If you know how the heaters are behaving, then it's just making sure all of these pieces, the Lego pieces, are connected to each other to create a simulated result. On the right-hand side, for instance, you are seeing one of our use cases, and you can see that the blue curve on the right-hand side is similar to the one on the left-hand side. Using this, you were able to create a digital simulation of the thermoplastic sheet. We can move to the next slide. All right. As I said before, in order to create a digital twin, data is also essential. So far, what I explained to you was mostly on the mathematical model side. So you need to understand the heating characteristics of the heating elements. You need to make sure the radiation equation is added, conduction equation is added, the geometric dimensions and the type of the materials added, but everything is in a perfect mathematical world. To make sure that the digital twin is calibrated or associated with the real machine, we need to collect data from the machine. So what kind of data can be collected? I mean, we can access to the PLCs of the machine, which controls the overall production cycle of the part of the machine. You can get sensor data. The sensor data could be the temperature value of the heater elements. It could be the voltage value of the heater elements. It could be some of the pyrometers, which measures the temperature of the surface of the thermal plastic sheet we would like to heat. It could also the pressure values, not in the thermal stage, but in the molten stage. Using all of this data and collecting real-time sensor data, now you have the option to calibrate your mathematical model to the real machine. Using the data, and the data is here, almost representative real-time data. That data can be used to capture your result and the real data in a single framework. And that is what we call the digital twin. We can move to the next slide. All right. So this is the section where I'm going to talk shortly about industry use case, and it's the Arçelik company. It is one of the largest appliances company in Europe, and generally European know the Beko brand rather than the Arçelik brand. Arçelik is mostly in Turkey. So this is a really huge company. They have almost like 7 billion euros revenue every year. They have more than 40,000 employees. And as far as I know, there's like 1,000 of them are just the R&D center. And in this example, in this webinar, I'll be focusing on Arçelik's refrigerator plant. So this refrigerator plant is located in a city called Eskişehir, and it is one of the largest refrigerator plant in the area, as well as Arçelik's largest refrigerator factory. This factory is using almost 50% of all the electricity for thermoforming process. You see, if you can improve the thermoforming process, you're gonna not just help the company to control their cost, it'll also support the sustainability goal of the company, because if you can reduce the amount of electricity usage, you can also reduce your carbon footprint. Sustainability goal. Can we move to the next slide, please? All right. Oh, Can you go back?
Yeah, sorry.
No problem. Appreciate it. So in total, Arçelik has 8 refrigerator plants, and the largest one are in Turkey. Here they are producing the liners. Liners are the part is is when you open the refrigerator door, you see these white walls, right? This is a refrigerator liner, all these white walls, and it is produced using the thermoforming machine. In total, Arçelik has 32 thermoforming lines, and that was my last number. They acquired a couple of new factories. Probably this number is even higher now. But what is critical here is that they are using almost 20,000 tons of plastics every year. That is tons, right? And that means you use a lot of, no problem, you use a lot of raw material, right? If your defects can be controlled, then you reduce your use of plastics. If you can control the heating process, then you can control your electricity, right? And here we did some early tests with Arçelik's one of Arçelik's thermoforming line, and you see on the left we collected data from the PLC. We also created an environment in which we can simulate how the temperature is occurring in our model. And you see 95% accuracy is achieved using our digital twin, where we created a calibrated system. You see the blue curves are what we are simulating on the left-hand side, and this reverse triangular shapes of the measurements. Right? This is very important because at first, I mean, we believe in ourselves, and so our initial model was like 90% accurate. Using the data we collected from the thermoforming line, we calibrated the heater elements. Remember, I was talking about the heater element curve. And here, Pablo, can I ask you to go back a couple of slides? I'm going to tell you when to stop. One more, please. One more. Yeah, here. Okay, heater. Heat. Yeah, this one. Remember this curve? So this curve on the left-hand side has a particular shape. It's like a parabolic shape from the y-axis point of view. And if you can calibrate the critical values on this curve, you have the option to control the temperature distribution on the heater array. That also means the temperature distribution on the thermoplastic sheet. Using our data from the machine, we were able to capture the behavior of the heater elements. And using this input, our digital twin created a couple of iterations. And at the end, a calibrated model just for that production line was able to be created. Now you can go to the slide view left. Yeah. No. Like 17. I guess it was 17. Yeah, perfect. Using that, we were able to create a characteristic behavior for the heater elements. So at the bottom center, you see a couple of blocks, like 200 at the top, 200 at the bottom, which I'm calling temperature top heater and bottom heater. These are calibrated using the data we collected from the machine. So we initially assume a curve, a characteristic curve. We did our radiation, conduction, finite element assessment just to create the initial result. Then we created a feedback loop. Here we optimized our output based on the input from the PLC of the machine. And at the end, the right figure is where we get a two-dimensional image of the real piece, which is 95% accurate at the point of the sensor data. And this is really important. I mean, so far, what you are seeing here on the right-hand side is not a infrared camera data. It's not a sensor data. It's just direct output of the digital twin. And using this, we can now do a lot of stuff. I mean, if you have a different targeted temperature profile that you would like to achieve, you can create a reverse heat transfer problem. to assign different values to different heater elements. Or let's say one of the heaters is broken, or maybe a couple of them is broken, and you need to change them. You see, it is really hard to stop a production line because you need to create a refrigerator, right? Here, digital twin can help you to compensate the error. If there is a defect on the machine and one of the heater elements are broken, the neighboring heater elements can also be used to compensate the missing thermal input. So you're going to increase this temperature for the neighboring elements, and at the end you can get still the same temperature output on the machine with an expense of maybe more electricity usage, but you're going to keep the production line running without stopping it for maintenance. All right, I have just one last slide, and then we can maybe move to questions if there are any. All right. So this is just the thermal side of the thermoforming process. In reality, the material is important because this is a thermoplastic material. And if it is softened, it can be hyperelastic / viscoelastic. So it is, unfortunately, also a non-linear material because of its polymer content. So material behavior can be also incorporated in the digital twin, especially for the molding stage, where we really give the final shape of our desired product. So in the molding stage, the pressure sensors can be incorporated in the digital twin because using the pressure values, we can control how much vacuum we creating, how much bubbling we can create on the system. Since now we have an understanding to improve the molding, you can go to your initial product design and maybe even improve your mold design, right? As I said before, cooling is also an essential part of the molding stage because we would like to reduce the temperature below a glass temperature so the shape that we give into the product stays the same. And there, using a special cooling channels, you have the option to reduce the cooling time as well. And finally, I talk about it a couple of times during the webinar. Sustainability aspect is also important. When we reduce defect, we have the company to control their cost. We have the company to reduce their raw material and electricity usage and their consumption. And that has a direct implication on reducing carbon footprint as well. So this is all from my side for today. I would like to thank you for listening and for being here. If you guys have any questions, you can maybe, I have it on the next slide, I guess. There should be, yeah, this one. Yeah, perfect. If you have any questions, you can always reach me from my email or maybe from my LinkedIn page, Simularge. Thanks for listening. Are there any questions?
Okay, yeah. Arhan, I have one question, if I may.
Sure.
What could be some of the limitations on the application of these digital twins? In your case, for the thermoforming activities, what are some of these challenges that you've been facing?
Yeah. Thanks. A good question. So when we create a digital twin, we are also creating a copy of the machine itself. So you see, I said I just incorporated heating elements on a machine, but in reality, the machine has a lot of components. It has a steel frame, and steel means it also gets heat up when we use thermal input on the thermoplastics. That part is not really added into the digital twin. If you see that you're uncertain, if you see that the accuracy is not the 90-95% level, then you might consider adding more details of the machine. Maybe some of the structural elements can be added into your model, and you can also assume they're also heated by this heating array, and that might be an option to improve your model. And second trick is that the material that you're applying heat input is not always pure, because of adding some recycled elements, because of the variation of the raw material supplier, the material properties vary. That means density is different, conductivity is different. Also, the surface finish is different. So surface finish is really important because in radiation, there are reflection, absorption. So those values are also critical, as well as tolerances might be different. You are working with a really rectangular thin sheet and it has a certain thickness, but this thickness might have some tolerances in certain directions. And in your model, since you cannot measure it, you're just gonna assume that the thickness level is somewhat constant. And all of these contributor factors will probably prevent you to get 100% accuracy, but 95% accuracy is not a big challenge. You can always use this as an input because the alternative is no model. That means 0% accuracy.
Okay, thank you very much. That was very
Sure.
insightful. Is any other question from the audience?
Okay. Oh yeah, Piotr. Piotr, go ahead.
I'm going to allow the microphone.
Sure.
Hello.
Hi, Piotr.
Thank you
How
for
are you?
the presentation. I was
Sure.
just want to ask you about the inspection part of the process. Is the when you talk about the optimization of the process, do you use the data from the inspection as the result of inspection? Because you
Yes.
can get different type of defects, and
Sure.
do you
Yeah.
classify those defects? And because you said also that there are different types of materials, density, and so on. So different defects occurs from different reasons, not because you change something in the process. So if you
Yeah.
could.
Yeah. Sure. Very good question. Thank you, Piotr. So remember, I was telling you that we are in the middle of the project, and then in the remaining months, we're going to be focusing on the defects identification. So there are a bunch of defects. There are sometimes coloring on some section of the part. There are some tears on the part after the molding process. You also see some hot zones and cold zones that are in unexpected regions. So you want some area to be warmer, but you see it's getting colder or vice versa. And these inputs are really useful because, example, if you say you see a tear on the surface after the molding process, that means that section is thinner than you anticipated, right? And thinner means it gets elongated more than anticipated. That also means it is warmer than expected because remember when you walk in the street in the summertime and you accidentally press on a gum and the gum gets longer and longer and longer because of the temperature difference. But if you do the same on a winter time, you don't see the gum stretching, right? In a similar fashion, if you see such defects, it is a candidate, I don't know, value, or it could be a clue for you that the temperature was not really properly defined. And for some coloring stuff, some black zones or other colors are typically material related. These are not the fault of the thermal part, but also an input for the machine operator. And in the remaining part of this project, we're going to be continuing with Siemens. Siemens is applying their infrared camera input and stereo camera inputs, and using their data collected from the machine, we're going to have some defect idea. Hey, we have some defects here, we have some cold zones here, we have some warm zones here, and these will be an input to me because I know in a good running system that temperature shouldn't be occur. I'm going to go back and say, hey, this heating element is not working properly. So that's an insight for me to go back and fix the problem. But yeah, of course, the defects are very important, and associating some defects to some of the reasoning is also another part of our project. Is it what you expected?
Yes, thank you very much. I look forward for your project. I will.
Thank you, Peter. Appreciate it. Yeah, back to you, Pablo.
Yeah, no, I raised my hands, I think, by accident. I don't have any more questions.
Yeah,
I'm sorry. I'm really sorry.
Suspicion. No problem. No problem.
Really sorry.
Okay.
So with that, Erhan, I think that is all. Thank you very much for your webinar. It was really interesting.
Sure.
And well, we'll see you around. Thank you everyone for attending. Yeah. And see you next time.
Yeah. Thank you guys.
Thank you. Goodbye.
Have a good day. Bye.